Hi, welcome to this short introduction to quantum field theory. This is a 12-week course and it will cover most basic concepts of quantum field theory, but also give you some introduction to more advanced topics such as renormalization and higher spin representations, while mostly focusing on scalar field theory. We will talk at the end about higher spins and the gauge principle, as well as non-abelian gauge theories. However, this is just a summary of what we want to cover. Today, I want to give you an introduction to the concept of quantum field theory, starting with the question, why do we need quantum field theory at all? Well, as the name tells you, quantum field theory is a description of quantum phenomena based on quantum mechanics. However, it also includes the concept of relativity, and we will discuss later at length how the concept of the field is unavoidable once we start talking about relativistic phenomena. However, here I just want to give you an argument why quantum mechanics alone is insufficient when we talk about relativistic systems. Let's assume we have a box of size L, right? We know that in quantum mechanics there is a fundamental principle at work that it's called the uncertainty principle, where we can't really tell whether a particle is localized in a particular space, location, at the same time as saying, well, the particle has a well-defined momentum. The better we resolve this spatial location of particle, the worse the resolution in the momentum space will get. We can rewrite this. I mean, here this h is just a constant. This the Planck's unit of action, the Planck's action constant, h bar, and we can rewrite this inequality as saying, okay, the momentum is bounded from below as h divided by the uncertainty in the position space. So now thinking about our box with a particle inside of size L. Well, do you remember the Little Prince, right? When the pilot is drawing the sheep for the prince, and in the end he draws a box with a few holes inside and says here the sheep lives inside of the box without really drawing the sheep. So that satisfies the Little Prince, as you might remember from the book. And the interesting thing, or a very philosophically smart thing here, is that fundamentally our world is really governed by the information we can obtain, right? So if we can't probe inside that box, we can really have anything happening in there. In a similar way, we say, okay, this particle can do whatever it wants, but we know that it really lives inside the box of size L. And if that is true, we know that its momentum uncertainty is larger, just rewriting this inequality, is larger than this minimal value h bar divided by the L, the size of the box. Okay, this is one step. Now we bring in relativity. There we know that the momenta are related to energies, essentially at large momenta. The energy and momentum are more or less the same up to a constant. If we divide energy by the speed of light, we basically get a momentum for a highly relativistic particle. And now we can substitute delta E for delta P, and so we know that energy uncertainty on that particle is larger than, again, h bar c divided by the size of that box. Now, let's assume we can choose different boxes or vary the size L of the box, and we can shrink that box down, right? So shrinking that box down makes our uncertainty in energy of that particle that lives in that box larger and larger. So we can now ask the question, what happens if this uncertainty in energy gets larger than m or 2mc squared, right? If you remember from relativity, mc squared is the rest mass of a particle with mass m, or rest energy of a particle with rest mass m. And that is fundamentally something happens when this inequality is actually saturated. So if our energy uncertainty is larger than the rest mass of a particle that we are observing, we can't actually tell if there's one particle inside that box or if there are two particles inside that box, or if we further increase the uncertainty in energy by decreasing L, we have even less certainty how many particles are actually living inside that box, which fundamentally tells us that something breaks down, and the thing that breaks down is essentially the conservation of particle number. Yeah, so bringing in relativity into the game and combining it with quantum mechanics tells us that there is an energy and corresponding length scales for a particle of a given mass m, where its particle number is not conserved anymore. So we can't really use the concepts of pure quantum mechanics, where we observed a particle, and the formalism is such that this particle always stays one particle. If we observe three particles, they always stay three particles. So quantum mechanical principles break down at a certain length scale, and we can define this length scale by rewriting again this inequality, substituting back the energy and length relations. We can derive this inequality by saying that there is a length scale at which for a particle of mass m, the quantum mechanical concepts break down. This is h bar over m times the speed of light c. So essentially, it's inversely proportional to the mass of the particle, and it's called the Compton wavelength for a single. And this is the wavelength where the single particle description fails. Now we can also say that we can observe that for a particle with mass me, let's say with the mass of an electron, the Compton wavelength is larger than for a particle with the mass of the proton. So if we look at the breakdown of the theory in terms of length scales, the electrons will start to essentially behave or show those phenomena of the particle number breakdown earlier than, say, protons. That is just related to their rest mass. If you remember quantum mechanics, there is also a scale that is relevant for quantum mechanics, namely the de Broglie wavelength, h bar, divided by the momentum of the particle. And naturally, this scale is larger because the momentum is always smaller, smaller than the rest energy of the particle. Yeah, and here we have a larger length scale at work, and this is the length scale where we have wave phenomena of particle matter. So where matter wave phenomena start to play a role, such as interference, depending on the momentum of the particles, and they depend on the mass, but also on the velocities. The slower moving particles will exhibit stronger wave-like phenomena than faster moving particles. Good. So that is the side question here: which of the scales is larger? And yes, the de Broglie wavelength is always larger, since the momentum is always smaller, let's say, than the total rest mass of the particles, since we have particles that move with velocities that are slower than the speed of light, right? So we have here something that goes as v times m, and v is always smaller than c, right? Gut. The second very important concept that plays a role besides the quantum merger between quantum mechanics and relativity in the theory of quantum fields is locality. Yeah, it's essentially the basic principle of relativity, but now combined with quantum mechanics, we will see that there is an option, or there will be the possibility of creating particles. And locality in this regard also means that all particles in the theory and in the universe are created equal. What I mean by that is that if I create pairs of particles, they are created in pairs, we will discuss it later, but if I create, for example, an electron and an anti-electron, that is called a positron, somewhere in the universe, maybe in a highly energetic environment, in some laser or high energy astrophysical phenomenon, it's the same as if I created in the Large Hadron Collider or in any other high energy experiment on Earth. And this particle, the electron and positron, will have the same charges, exactly the same masses anywhere where I create those particles. And this is what I essentially call a field theoretical locality, that you can't really have variations of those particles anywhere you are in space and time. The quantum numbers essentially are unchanged. Now, we need a theory that provides us with a pool, essentially, of things that are basically excitable quantities, where we can go up in energy levels, if you will, and by that create excitation quanta of a property, or of a excitation quanta of something that will exhibit the same quantum numbers. And this is a very heuristic argument why we actually need a field that will permeate the entire space and time, and exciting that quantum field will provide us with the same kind of quantity, or with objects with the same properties, no matter where and when we excite them. Yeah, this is quite a heuristic argument. This locality in space and time and universality of creation of particles brings us to the concept that we actually need fields. So fundamentally, we will have to deal with continuous properties that span the entire space-time. Good. Now this already brings me to the next point. What is actually quantum field theory? So as you remember, probably in quantum mechanics, the classical degrees of freedom, such as positions, that we know from the mechanics, Newtonian mechanics course, become operators. They get a little hat, operators. If you can always think of an operator as some sort of generalized matrix with finitely many or infinitely many entries, but it's some sort of matrix. And the act on a vector space, the so-called Hilbert space that describes the states of particles or systems that we described. Now in quantum field theory, we have operator-valued functions of x and t. Now what it means is that we do have operators, but they are continuously spread throughout the space, which gives us automatically, in any case, infinite degrees of freedom, and this brings in certain technical difficulties that we will deal with and discuss at length later. Now, as we said, QFT is based on the principle of locality. Then symmetries will play an important role, whether a system is spherically symmetric, translational, invariant, and so on. And we also have locality in energy that we call the renormalization group flow. And that means that in the technical term, when we talk about particle interactions, that if we move between energy scales, new kind of phenomena that could induce complicated interactions of many particles with each other will be suppressed and not really play a role when we consider a particular energy scale. And the dominant interactions would be quite simple, mostly interacting of 3 and 4 particles with each other, and maybe those could be the same particle or those could be different particles, but topologically the interaction will be dominated by quite simple terms, making the fundamental theory, once you fix an energy scale and zoom in and study physics at this energy scale, quite simple. Or if, in other words, if you increase your resolution of observing a particular fundamental theory, that the theory in the typical case gets simpler in its fundamental description. Now, finally, what is quantum field theory used for? And basically, any relativistic system, as we said, as a relativity and quantum mechanics have to be combined, needs to be described by quantum field theory. This is obviously anything that has to do with high energy physics, where the energies approach the mass scales of the particles involved. This happens often in astrophysical phenomena, where stars and explosions in space reach very high energies, or densities become very, very large in certain astrophysical objects. Cosmology as a subject in general, when we deal with the early cosmology, early universe, extremely high conditions, highly related to high energy physics, as the energy scales are very similar to what we reach in colliders, and higher, but this is like the realm of physics that we actually can test, probe, and discuss and study. Then condensed matter theory, interestingly, is also strongly, really very strongly dominated by quantum field theory, as very many phenomena such as superfluidity or superconductivity are quantum phenomena where particles in the lattice behave in a quasi-relativistic manner, and so we definitely need quantum field theory to describe their behaviors. Then quantum gravity is the next holy grail that we haven't found yet, let's say, where we try to merge the concept of locality, quantum mechanics, and general relativity. Yeah, so far we have really only talked about special relativity, but talking about general relativity in the concept of curved space-time is a whole different challenge, where we will also discuss why in certain situations we also would need to resort to another theory that is beyond quantum field theory, and that's a big subject of ongoing research today. Okay, so let me come to a couple of practical things that we will need in this course, and here a very helpful notation that we will use is the so-called system of natural units. Let us talk about a few fundamental constants in nature, and they are used to actually describe and measure the things we see, such as the speed of light. Speed of light is a very useful gauging mark for many phenomena in nature, as it is the largest speed possible in the universe, and it has obviously the units of length divided by time as any speed, and we can use it to describe a length scale. As we say, how long does it take the light ray to go from this point to that point? And this measures a length scale, but it can also be used to measure time if we fix the length scale and observe the light rays going back and forth, let's say. It is can be used essentially as a ruler and a clock at the same time. Then there is another constant, that we saw above, that's like the quantum of action, the Planck quantum of the action. We can derive its units from maybe from the uncertainty principle, delta p times delta x bigger than h bar, right? And we find that it's length squared times mass divided by time. That's the action units of action. So when I draw these squared brackets, I always mean what is the unit of a certain quantity. And then there's the Newton constant, where we can find the units, for example, from knowing that the gravitational force is equal to the Newton constant times m1 times m2 from two bodies divided by their separation squared. From there, we can figure out what the units of this quantity are, and they are in terms of length, mass, and time scales, length cubed divided by mass times divided by time squared. So those quantities provide us with a system of units and rulers that allow us to measure in all phenomena in nature, because they contain the length scale, time scale, and the mass scale. And with those three things, we can describe anything that surrounds us. Now, in theoretical physics, it's very convenient to set those quantities equal to 1 to simplify our expressions. And this is called natural units. Now we can look at this and say, okay, setting c equal to 1 immediately fixes length to the same, brings length on the same footing as time. This is actually physically completely understandable. As I said before, we can use the speed of light to measure length in terms of how long a light ray travels from one point to another, or how long it takes for a light ray to go in between 2 points back and forth. That measures the time. And if we know the distance between them, we can basically define a time here. So length and time are interchangeably used and linked by the speed of light. In a similar way, mass, once we insert set the units of length and time equal, we can use the fact that we want to set h bar to 1. Then we have L squared divided by time is just L times mass is equal to 1, which means that mass is inversely proportional to length. And here, this is also fundamentally connected to the Compton wavelength here. As we said before, h bar divided by c1 over m is a Compton wavelength. Setting this equal to 1 tells us that the Compton wavelength is just the inverse mass. Yeah, and this is really what we discussed above. Particles with larger masses should exhibit this breakdown of conserved particle number at shorter length scales. And this is directly encoded in this compact expression in natural units for the Compton wavelength. Well, now I just want to briefly give you an intuition for the length scales we talk about in the universe and describe them with quantum field theory. For example, the mass of the proton is a useful length and mass scale, as we can describe physical quantities as a gram of matter by the number of protons that is inside. That's about 10 to the 23. And it's a physical unit. It's not a man-made arbitrary unit as a centimeter, meter, or something. And the unit of fundamental physics is very often referred to as electron volt. It's the energy unit that is needed to accelerate an electron to give it a volt of energy. And the proton mass is pretty exact, pretty much 10 to the 9 electron volts, and that it's abbreviated as giga electron volt, GeV. Yeah, this is a very useful kind of measuring stick for masses. And as we said, 1 divided by GeV is a certain length scale that corresponds to 10 to the minus 15 meters, and that is roughly the size of the proton in quantum mechanical terms. Then, going to larger and larger masses, we will find there is another scale that is 19 orders of magnitude larger than that, 10 to the minus 35 meters short, very short distance, very high energy. But here quantum phenomena from gravity would start to play a role, and this is called the Planck scale. We'll briefly talk about how this comes about in a second. Now, moving down, we can go to lower masses and larger length scales, such as the electron mass. Electron mass is about 2,000 times smaller than the mass of the proton. That's around the MeV scale, the mega electron volt scale. Length scales associated to that are 10 to the minus 12 meters. This is something closer to the atomic scale. Now going further down in this energy can bring us to the largest distances and shortest and smallest masses that we can actually think of. And 10 to the minus 33 electron volts is an insanely small mass and corresponds to 10 to 10 light years. So basically 10 years for light. That is essentially the size of our universe. So quantum field theory spans, or we think that quantum field theory is applicable across all those length scales, covering over 60 orders of magnitude. More over 50 orders of magnitude in energy. Finally, I just wanted to mention why when we think that also the quantum field theory description has its limitations when we talk about gravity. If you remember the equation for the escape velocity, 2 times g Newton times mass divided by the radius of an object, square root of that gives you the escape velocity. So we know that an object, when you make it heavier and smaller, it shows the phenomenon of creating at some point a Schwarzschild radius beyond which you can't escape, which in classical gravity, without involving general relativity yet, means that the escape velocity from the object becomes equal to 1 and not even light can escape from it. So if we say that the escape velocity should become 1 for an object, for a fundamental particle, then its mass will essentially be the we can solve for its mass and radius in terms of its Compton wavelength by the use of the Newton constant natural units. And this is just 1 divided by a mass scale squared. This mass scale is about 10 to the 19 GeV. And here we reach a point where for the particle with that Compton wavelength and its mass, the escape velocity would become 1 and the particle would be essentially described by a black hole solution. And this is not something that we can trivially describe in quantum field theory, where we therefore believe that quantum gravity phenomena will start to matter at a mass and energy scale of 10 to the 19 giga electron volts, where even the fundamental particle would be equivalent to a black hole. Now, good. A couple of technical things to remember for this course, and we will cover them in the next lectures in more detail, but just as a brief reminder of what we will talk about is classical mechanics. Fundamentally, classical mechanics deals with the Lagrange function. That is the integral over the Lagrange function. Time integral over the Lagrange function gives us the action, and the fundamental principle governing the physical world is the principle of least action. Systems tend to minimize the action, and when you minimize the action, you find that this gives us a particular equation of motion for the system that can be derived from this argument of this integral here. So the derivative with respect to the temporal position change, q dot, is called the generalized momentum. The time derivative of that is equal to the derivative of the Lagrange function, or minus the derivative of the Lagrange function with respect to the position is equal to 0. This equation provides us with an equation of motion for a given system that we are studying that has this particular Lagrange function, and we will set up a couple of Lagrange functions for simple systems. There is also another important function, the Hamilton function, which can be found by Legendre transforming the Lagrange function. The Legendre transform is essentially a local tangent at each point in the momentum and position space. It is found by taking the generalized momentum, the LdQ, multiplying it by the derivative of the space position Q, multiplying by Q dot, and subtracting the Lagrange function. If we have multiple particles in the complicated system, we have to sum over the particle and momenta and positions. Now, derivatives of the Hamilton function with respect to position and momentum tell us what the differential equations for the evolution of the positions and the momenta of the systems are, and that defines as behavior of the system in the so-called phase space. The phase space is a six-dimensional space. For three-dimensional space, physical space, the phase space is a six-dimensional space of momenta and positions of all the particles involved. Now, there's another concept, the so-called Poisson bracket in quantum in classical mechanics, which is written with these curly brackets. So a quantity f and g has a Poisson bracket that is defined by these derivatives of the f and g with respect to positions and momenta, and subtracting the flipped derivatives df. The f is here, f is derived by q, and here there's derivative with respect to p, and vice versa with g. So and we can prove, or one can prove, that the Poisson bracket for positions and momenta mutually vanish, while the positions momenta of particles give us a Kronecker delta, which indicates that for the same particle we get a 1, and for different particles we get a 0 here. And we note that this spans can be seen as a certain area element in the phase space of momenta and positions of a particle, and we will come to this in a second. In quantum mechanics now, we take these momenta and make them into operators, as you remember from the quantum mechanics course, and they act on a Hilbert. They are operators that act on a state in the Hilbert space, a vector space. So any function on the phase space now can be seen as an operator that acts on the Hilbert space. Any function that depends again on Q and P. And technically what we also do is promoting this Poisson bracket to the so-called commutator, multiplying it by I divided by h bar, and including a minus sign for technical reasons. But the operators now have a very similar relation as the Poisson brackets had with the classical quantities. They are commuting when you have positions or momenta, and they give you, and they don't commute if we look at the positions and momenta of particles of the same particle. Yeah, then the commutator of a particle A with Q and P is I h bar, and that in quantum mechanics, as we said before, with the Poisson bracket, there's fundamental area or volume in the phase space, and in quantum mechanics, this fundamental non-commutativity of positions and momenta defines a finite volume in phase space that we can't resolve beyond. We can change its shape by measuring positions or momenta better, but fundamentally there's an irreducible volume in phase space that describes our limitation of actually measuring quantities that are so-called conjugate quantities and have a non-vanishing commutator in quantum mechanics. Well, also in quantum mechanics, a very important equation is the Schrödinger equation, where the time evolution of a state, psi dot, multiplied times I h bar, is described by the multiplication of the so-called Hamilton operator, the energy operator that we will discuss, or the Hamilton function that is the Legendre transform of the Lagrange function promoted, where the quantities have been promoted to operators, acts on the state psi. And we will also discuss how to treat those time evolution of particles in a much greater detail. Finally, we have to remember what is our formalism about special relativity and what is a convenient way of writing special quantities and special relativity, namely using so-called four vectors. Vectors are invariant quantities, invariant or can be or are physical quantities that can be used to construct invariants, such as the length of the vector that is the same in all reference frames. It's absolutely known, or it's absolutely familiar to us in classical mechanics, where a certain length arrow of a certain length will stay the same no matter from which coordinate system we look at it. Similarly, in quantum and special relativity, we promote this to a space-time concept. We add an additional component for time. We denote typically it's this time with the zero component, and the three components for space, x, 1, 2, 3. And often the indices, instead of I, J, that are reserved for spatial indices, are then replaced by Greek letters like mu and nu for the space-time indices 0, 1, 2, 3. Right. The vectors can be covariant, where this mu sits in the has a lower case, or is it at the lower at the bottom of the variable, or they can be contravariant when they are the index is shown in the upwards position. And this essentially just means that we can apply the multiplication of those objects in a different way. For example, in order to make a contraction, to make a connection between those two vectors, we need to have a contravariant and covariant vector. And this is done by applying the matrix of the metric that is typically called eta to the vector. That is, for example, contravariant, applying a matrix vector here. Matrix metric here makes it into a covariant vector. In special relativity, the metric matrix is a simple matrix with a 1 in this first position, in the temporal position, and negative ones on the diagonal purely spatial positions. Multiplying two metrics together, we can show that is just a multiplication of those two matrices that give us just the diagonal matrix that we denote with a Kronecker delta mu nu. A very common vector to be used is the four-dimensional momentum vector, with the zeros component in containing the energy and the momenta, spatial momenta, sitting in the spatial components. So if we do the contraction with the we do the contraction of the indices like that with the covariant and contravariant vectors, we get an invariant that is the same in all reference frames, namely the rest mass of the particle, m squared. And we see that here we get the e squared from the first component, then the negative sign from the metric, and we get the p squared. So e squared minus p squared is equal to m squared. Rewriting this in terms of energy, e squared is equal to m squared plus p squared. Now we can restore actually the speed of light just for familiarity. So e, if we take the square root, e is m squared times c to the fourth plus p squared c squared. This is just a relativistic energy mass momentum relation, setting the momentum, for example, to 0 for a particle at rest. This term goes away, and we know that e is just, we can take the square root and we find that e is just mc squared. This is the famous Einstein formula for this energy momentum relation. Finally, this is something one can do at home, is to look at the principle of least action for the Lagrange function and see how this equation of motion is actually derived by varying this functional, the functional as being the integral over the Lagrange function, and setting its variation to 0. This is the principle of least action. Saying system tends to minimize the action that it's using. Setting that to 0 tells us essentially a condition for gives us a differential equation for momenta and positions of the particles or of any system that has a particular Lagrange function that will describe the system, and we call this equations of motion. This is something here we can check at home that this derivation is indeed valid, and the equation of motion for a classical classical mechanical system is indeed given by that. Good. With this, I would like to conclude this introduction, and we get to the classical field theory, derivations and equations of motion, and conserved vector quantities in the next lecture. Thank you.